In this video, we will continue our discussion of physical methods of microbial control with our focus on filtration, osmotic pressure, and radiation. Filtration is a technique that removes microbes rather than killing or inhibiting them. Filters may be used to remove microbes from liquid or air. Liquids may be passed through man-made filters. The filters may be made of plastic or cellulose materials. A common material is nitrocellulose. The pore size of the filters can be controlled and may be made small enough that it acts to trap all bacteria, viruses, and even large protein molecules. Heat-sensitive liquids such as liquid vitamins, culture media, antibiotics, and vaccines are sterilized using filtration. Air may be filtered through high-efficiency particulate air filters, also known as HEPA filters, that act to remove almost all microorganisms larger than 0.3 micrometers in diameter. HEPA filters are used in places such as operating rooms, biological safety cabinets, and rooms that house patients with airborne diseases such as tuberculosis or immunocompromised patients such as AIDS patients or burn patients. Again, please be aware that filtration neither destroys nor inhibits microorganisms, but rather removes them from the substance. High concentrations of salt and sugars are also utilized to inhibit the growth of microorganisms. High salt or sugar concentrations inhibit microbial growth because they create hypertonic environments that cause a loss of water from microbial cells. As the cell loses water and becomes dehydrated, the metabolism of the cell comes to a halt. Some microorganisms, such as facultative halophiles and fungi, are capable of tolerating higher solute concentrations. High salt and sugar concentrations are used to preserve foods such as jerky, jams, jellies, and honey. Radiation may be used to control microbial growth as well. Radiation will affect cells differently depending on its wavelength, intensity, and duration of exposure. Radiation is classified into two groups: ionizing radiation and non-ionizing radiation. Ionizing radiation includes those forms of radiation that have sufficient energy to cause the ejection of electrons from molecules as they strike them. The loss of electrons results in the formation of ions. Ions can act to disrupt hydrogen bonds of proteins and nucleic acids, may cause oxidation of double covalent bonds, and may also cause the formation of hydroxyl ions, one of the four toxic forms of oxygen we discussed in Unit 3. Ionizing radiation includes gamma rays, electron beams, and X-rays. All of these forms have shorter wavelengths, thus they are higher energy forms of radiation. Their higher energy permits them to penetrate materials easily. The damage caused by the radiation is lethal. Thus, radiation is a microbicidal technique. Although all three forms of ionizing radiation can cause damage to microbes, not all forms are utilized on a regular basis as an antimicrobial method. Electron beams are produced by cathode ray machines. Electron beams kill microorganisms within a matter of seconds, but are limited in their ability to penetrate thick objects or objects coated with organic material. Gamma rays are more effective in penetrating materials than electron beams, but require hours to kill microbes. Gamma rays effectively kill microbes, insect, eggs, and larvae, and kill the cells of fruits and vegetables to prevent spoilage and over-ripening. X-rays penetrate materials well, but require such an extensive amount of time to kill microbes that it is not used. Ionizing radiation is an effective alternative used to sterilize heat-sensitive materials. Ionizing radiation has been utilized in the food industry to sterilize food to prevent spoilage, and medically to sterilize pharmaceuticals, vaccines, tissue grafts, and heart valves, as well as disposable dental and medical supplies such as gloves and syringes. Non-ionizing forms of radiation have longer wavelengths and thus less energy than ionizing forms of radiation. Therefore, they do not penetrate material well and do not have the required energy to cause the ejection of electrons. So they do not form ions. Ultraviolet light is an example of non-ionizing radiation. Ultraviolet light causes damage to cells by causing electrons to be excited enough that they cause the formation of new covalent bonds within proteins and nucleic acids, which causes a change in their three-dimensional structure. The most effective wavelengths of UV light are between 240 to 280 nanometers, with the most damaging being at 260 nanometers. At 260 nanometers, UV light causes a bond to form between adjacent thymine bases in DNA, forming what are referred to as thymine dimers. Thymine dimers inhibit replication and transcription, thereby interfering with metabolism, which leads to the death of the cell. While UV light is microbicidal, it is limited in its use because of its poor penetration. UV light does not have sufficient energy to pass through materials such as glass, metal, cloth, plastic, or paper. Microorganisms are killed only when they are directly exposed to the rays. Because of its poor penetration, UV light, or non-ionizing radiation, is only used as a form of disinfection. UV lights are used for disinfection in food preparation areas, hospital rooms, and schools, and has also been used to disinfect liquids. Liquids must be passed in a thin film that is directly exposed to a UV lamp to effectively disinfect the liquid. UV lamps have been used to disinfect wastewater and water at city pools.